Hello and good afternoon friends, welcome to CEC live lectures. Dear friends, today in this session we are going to continue with our previous lecture on aldehydes and ketones. We would be discussing in detail on the following topic, and if you want to have question answer round, if you want to ask questions on this particular topic, then you can call right in the studio. Before that, I would like to tell you all that if you want to ask questions, you can definitely ask questions, but the expert who is going to deliver today's lecture is Dr. Aparajita Chauhan. Dr. Aparajita Chauhan is Associate Professor in Department of Chemistry, Sri Aurobindo College, University of Delhi. Dr. Chauhan has written a number of books. If you get time, please do read them and enlighten yourself in the area of chemistry. Dear friends, for asking questions from Dr. Aparajita Chauhan, you can contact her through our toll-free number. Our number is 1-800-110-430. Our toll-free number is 1-800-110-430. This is the toll-free number through which you can call us and talk to Dr. Aparajita Chauhan, but you are requested to call in the last 10 minutes so that the lecture goes uninterrupted, and in the last 10 minutes, whatever you have learnt and whatever questions revolving around you could be answered. Hello ma'am, welcome to the lecture.
Thank you. Hello viewers, in continuation with our lecture on aldehydes and ketones. In previous lecture, we had discussed some naturally occurring important carbonyl compounds, that is aldehydes and ketones, and then the nomenclature of aldehydes and ketones. We had also started with methods of preparation, and we will be continuing from there. When I talk of carbonyl compounds, as I told you in my introductory lecture, that carbonyl compounds are those compounds which have a carbonyl group in them, that is, they can be acids and acid derivatives as well as aldehydes and ketones. So today when we talk of carbonyl compounds, if I refer to a carbonyl compound, I'll be referring to aldehydes and ketones. So without further ado, I will start with the methods of preparation. First, we'll quickly revise what we did in our last lecture. So when we talk of preparation of aldehydes and ketones can be prepared from alkynes by, first method is by mercuration, demercuration. So please remember, when we do this reaction, the overall reaction is anti-addition of water according to Markovnikov's rule, resulting in enol formation. So when we get this enol, this then rearranges, or then this tautomerizes to give us a ketone. The salient feature of this reaction is that a cyclic mercurium ion is formed in this. Since a cyclic mercurium ion is formed as an intermediate and no carbocation is formed, there is no possibility of rearrangement in this reaction, and the yield of the ketone formed is very high. Second thing that you have to remember in this reaction is that since water is adding across the triple bond according to Markovnikov's rule, that is, OH is going to that carbon which is having less number of hydrogens, in all the cases except acetylene, we will be getting a ketone. So that's where we will be getting a ketone. So this is very, very important. When we do oxymercuration, demercuration of acetylene, we get acetaldehyde. Next method of preparation is by hydroboration oxidation of alkynes. That is, in this case, we will treat alkyne with boron, boron hydride in THF, followed by alkaline hydrolysis, when we'll get an enol. In this case, what we have to remember is that the overall reaction is a syn addition, and the addition of water molecule is anti-Markovnikov. Whereas when we are doing mercuration, demercuration, then the addition of water is Markovnikov's, and there the addition of water is anti-addition, whereas in this case it is a syn addition. Now boron is an electron deficient species which we had discussed in detail in last lecture. It will act as an electrophile, and it will go and react with that carbon which is having less number of hydrogens, less substituted. So what we find here is, since this is a symmetrical alkyne, it can go to either of the carbons. to give us a boron substituted alkene, and now this boron substituted alkene on alkaline hydrolysis gives us a enol. This enol torsiomerizes to give us a ketone. If it is a terminal alkyne, then please remember boron will add to that carbon which is having which is least substituted. Whereas if we do mercuration demercuration, then please remember OH will go to that carbon which is more substituted. So this is where the difference lies in. That is, when we are doing mercuration demercuration, the addition of water is across the triple bond is according to Markovnikov's rule, that is OH is going to that carbon which is less substituted. Whereas when we are doing reaction that is with diborane followed by alkaline hydrolysis, then in that case water adds across the triple bond according to anti-Markovnikov rule, giving us an aldehyde. So what can we conclude from here is that if we do hydroboration oxidation of an alkyne having a terminal triple bond, then it results in the formation of an aldehyde, whereas if we do oxymercuration demercuration, then in that case a ketone is formed. And these two methods are important methods for preparation of aldehydes and ketones. So now let us look into two questions, follow-up questions. The first question is that which of these alkynes, that is 1-butyne, 2-butyne or 2-pentyne, what will be the products formed when we do the reaction with of 1-butyne, 2-butyne and 2-pentyne with mercuric ion catalyzed addition of water or by hydroboration oxidation. So what we find is that since 1-butyne is a terminal alkyne, that is, in this case the triple bond is in the corner. So please remember, as I have told you, that when we do acidification with mercuric ion, then we will get a ketone, that is, we'll get 2-butanone, and when we will do hydroboration oxidation, then we will get butanol. Now 2-butyne is a symmetrical alkyne, so in both the cases we will get a ketone. Similarly, we can work up with 2-pentyne also, we will get 2 ketones here because this pentyne is not symmetrical, it is unsymmetrical. The next thing that is very often asked is that which is that alkyne, only one alkyne with which we do the acid hydrolysis or mercuric ion catalyzed hydrolysis, that is addition of water, it gives us an aldehyde. So please remember, as I said just now a few minutes back, that it is acetylene, and acetylene on hydrolysis as well as acid hydrolysis as well as mercuric ion catalyzed hydrolysis will give us acetaldehyde. All other alkynes will give us ketones when we do either do acid catalyzed hydrolysis or mercuric ion catalyzed addition of water. Now the next method of preparation is that we can prepare aldehydes and ketones even from alkenes. How do we do that? We can do it by reductive osmolysis. That is, what is the reagent which is bringing about the reaction? It is ozone, and then we are doing the reduction with zinc. So when ozone in dichloromethane is passed through alkene at low temperature, cycloaddition of ozone takes place, which acts as an electrophile. And then when we do the hydrolysis, or then we do the reduction with zinc, we get a carbonyl compound. Now the question arises, when will we get an aldehyde or a ketone? This depends on the structure of the alkene. That is, if alkene is unsubstituted, has an unsubstituted carbon, what we mean here is that if the carbon containing the double bond is primary, then the double bond will be oxidized to formaldehyde. And if it is monosubstituted alkene, that is the carbon containing the double bond is secondary, then we will get an aldehyde. And if it is a disubstituted alkene, that is a carbon containing the double bond is a tertiary carbon, then that double bond will be oxidized to ketones. So let us look into the structures, what I mean by this when I said a monosubstituted or a disubstituted alkene. So if you look into this structure, this carbon here, which is containing the double bond, is a secondary carbon here. And what we will get is, since it is a secondary carbon, that is, it is attached to one alkyl group. So the simple way of doing it is, without going into the mechanism of the reaction, is we break the double bond from here, we will get two fragments here. And when we get two fragments here, what we find here is that we will add oxygen to each fragment. So this will result in the formation of acetone as well as acetaldehyde. Now, if I look into the next example, this is a simple way of doing it without going into the mechanism, that whatever alkene you have, from the double bond, you break it into two parts, each part containing a double bond. When this is done, we add oxygen to each fragment to get the products. So if we take an example of 3-methyl-1-butene, then what we find is that this carbon here is not substituted. It is only attached to hydrogens. So in this case, what we've said is that if we have an unsubstituted carbon, then we'll get formaldehyde. So what we find here is that if we break the bond here and we attach oxygen to it, we will get formaldehyde. Whereas if I look into the second part of this, the second fragment, then what we find is that this is monosubstituted carbon. That is, on one side it is attached to hydrogen, and the second group present here is this alkyl group, which is your isopropyl group, iso grouping here. So what we do is, when we do the oxidation with ozone, what we find is that when we do the cleavage with ozone, what we find here is that this bond breaks and we get formaldehyde from this part, and we get 3-methyl isobutyl aldehyde, or we get 2-methyl propanaldehyde in this case, which is the IUPAC name of this compound. So what you have to remember is, we have to break this double bond and add oxygen at each fragment that we are getting. Now if we look into the mechanism of the reaction, then what we find is, if we look into the resonating structures of ozone, then what we find is that ozone is made up of 3 atoms of oxygen. Here, one of the oxygen is having a positive charge, that is, it is electron deficient, whereas one is having a negative charge, so from here it can act as a nucleophile. Whereas what we find is that this ozone is overall acting as an electrophile, since when we talk of the alkene, this alkene has a double bond here. So that means this is an electron-rich area. So there should be a bond formation between one of the oxygen atoms of the ozone with this double bond. And double bond will act as a nucleophile, and the oxygen will act as an electrophile. Now the question arises, which oxygen will act, which will be the electrophilic site in ozone molecule. This cannot be, because this has a negative charge on it, so this would be the nucleophilic site. Among these two oxygens, if we compare, this oxygen again will be difficult to be a electrophilic site, because it is already forming 3 bonds. So which is the best oxygen at which can form a bond with this double bond is this oxygen, which is on this side. And this now simply adds across this double bond, that is, this double pi bond breaks from here, it makes a bond here with this oxygen, and then this carbon becomes electron deficient, that is, also this oxygen acts as an electrophile, it forms a bond with this carbon here, this carbon now becomes electron deficient, and this oxygen goes and forms a bond here, forming a monoozonide or a initial ozonide. Now, if you look into the structure of this monoozonide here, what we find in this is that there are 3 oxygens attached here, and there is repulsion between the lone pair of electrons on these oxygens. So this is highly unstable molecule. It isomerizes to give us ozonide. So this monoozonide or the initial ozonide cannot be isolated. How does it convert into this ozonide? First, what happens is it breaks into 2 fragments. That is, one fragment is the carbonyl compound, as we can see here. This converts into a carbonyl compound, and the other fragment is a ionized species. So first we get 2 fragments, and then these 2 fragments recombine to form a ozonide here. So the recombination is taking place here. This carbon here is electron deficient since it is attached to a oxygen with a positive charge. This oxygen pulls the pi electrons towards itself, and it collapses on this oxygen, neutralizing the positive charge. And this oxygen, this here, acts as a nucleophile, and it comes and makes a bond with this carbon. And next point what we find here is that this oxygen will attack this carbon, which is now electrophilic, through the lone pair of electrons, resulting in the formation of ozonide. Now, once ozonide is formed, it reacts with zinc. So what does zinc do? Zinc reacts with this oxygen, giving us zinc oxide. At the same time, what happens is that this double bond from here breaks, it goes back here to form a double bond, and this bond breaks from here and it goes here to form a double bond. So what we find is, this is how the cleavage takes place. First, this oxygen reacts with zinc to form zinc oxide, and then the bond cleavage takes from here to result in the formation of one carbonyl compound, and then if it cleaves like this, then we get the second carbonyl compound. So this is how we get aldehydes and ketones from alkenes. So what you have to remember is, the simple thing is that we will break the double bond, make 2 fragments, and then to each fragment we will add an oxygen when we will get the resulting product, which may be an aldehyde or a ketone. So let us look into this question now. This question asks us that among these 3 alkenes that we've put here, this is 2,3-dimethyl 2-butene, this is cyclohexene, and then this is cyclohexadiene substituted, cyclohexadiene tetramethyl substituted. So what we find here is, as I have told you, we don't have to go into the mechanism of the reaction. Please remember, what you have to do is, wherever you have a double bond, we have a double bond here. So please break this double bond, and then to each fragment add oxygen. So if we do this, then what we find is, it is this 2-butene which will give us acetone on reductive ozonolysis. So this is a CH3 group, this is a CH3 group, and this is, we see attached to an oxygen here, we result in this molecule which is acetone. Now if someone asks us how would we do the ozonolysis of cyclohexene, then please remember, cyclohexene is a cyclic structure. So when we break the double bond, what we will have is, we will end up having 2 aldehydic groups in the same molecule. So in this case, we will get cyclohexane 1,6-diol. Whereas if we look into the third example, then what we find in third example is that here we have 2 double bonds, right? So what will happen? One cleavage will take place here, and the second cleavage will take place here, resulting in again a diol. So what we have here is 2 molecules of a diol, that is 1, 2, 3, 4, 5. So this basic compound is pentane, and we will get 2 molecules of pentane 2,3-dione. That is, we'll get a ketone here. Whereas in this case, we are getting 2 molecules here. Whereas if we talk of this molecule, then here we will get just one molecule of cyclohexane. It is hexane 1,6-diol. The ring structure will break, so it will be no more cyclic. The next very interesting method of preparation is, and it is quite important also, by oxidation of alcohols. We know that we have three types of alcohols: a primary alcohol, a secondary alcohol, and a tertiary alcohol. A primary alcohol is that alcohol in which OH is directly attached to a primary carbon. That is a carbon which is attached to either one other carbon or no other carbon. And when I talk of a secondary alcohol, then in that case, OH is attached to a carbon which is attached to two other carbons. That is, isopropyl alcohol is a secondary alcohol. Whereas if I talk of propanol, then it is a primary alcohol. And then we have a tertiary alcohol. But since tertiary alcohols do not have alpha hydrogen, they do not undergo oxidation. So what we are interested in is now the oxidation of primary alcohols and secondary alcohols. There are two types of oxidizing agents. One are strong oxidizing agents, like if I talk of an acidic potassium dichromate or acidic potassium permanganate. Then what we find are that these oxidizing agents are strong. So whenever we talk of these oxidizing agents, they will oxidize a primary alcohol to an acid and a secondary alcohol to a ketone. Whereas if we talk of mild oxidizing agents like Collins reagent, which is a mixture of chromium trioxide with pyridinium dichloromethane, or Corey's reagent, which is pyridinium chlorochromate, or PDC, which is pyridinium dichromate, then these oxidizing agents oxidize primary alcohols to aldehydes in absence of water. Please remember, we have to do it in a solvent like dichloromethane and not in presence of water. And please remember, whether we take a strong oxidizing agent or a selective oxidizing agent like Collins reagent, they will oxidize secondary alcohols to ketones. So in case of ketones, whatever oxidizing agent we are taking, we are getting a secondary alcohol is being oxidized to a ketone. So we do not have to worry about the oxidizing agent here. We have to worry in the case of primary alcohols, because primary alcohols on oxidation give us aldehydes, and aldehydes are more reactive towards oxidation, and they will immediately give us an acid if we use potassium permanganate or potassium dichromate. So what we do is we are using again chromium salt, but we are using them modified. That is, we can take a mixture of chromium trioxide with pyridine in dichloromethane, which is Collins reagent, or we can take pyridinium chlorochromate, which is PCC, or we can use pyridinium dichromate. The best part about these reagents is that it will oxidize an alcoholic group, but it will not oxidize a double bond or any other oxidizable function which is present in the molecule. So before proceeding further, let us look into the structure of PCC. What is PCC made up of? So when we talk of this, we are taking chromium trioxide in HCl. So chromium trioxide reacts to give us this chromyl chromate ion as well as pyridine. We get this complex chlorochromate, which then acts as an oxidizing agent in this reaction. So what happens is, this is a very interesting reaction. What happens in this case is, if we look into the structure of chromium here, this chromium is electron deficient because it is attached to electron withdrawing groups here. So it is an electrophilic center, whereas the lone pair of electrons on oxygen are acting here as a nucleophile. So what are we going to do here? Please remember, is a basic aim here is to introduce a good leaving group here, and then when this good leaving group will depart, this molecule can be converted into an aldehyde. So what we do here is that when this lone pair of electrons react with chromium here, we get this intermediate here. Now what we find is that in this, chromium is attached to too many atoms. So what happens is that this, and we get a protonated oxygen, we get a positive charge on oxygen here. So we get a protonated OH here, protonated OH. So what happens is now a base will transfer this H from here to this one of the oxygen. So what happens here is a proton transfer takes place. This proton transfer can be internal, or pyridine can help in, or the water molecule can act, will help us in transferring this proton from here to one of the oxygens. When we do this, we get this complex. Now what happens is, in this case, this oxygen goes back, the lone pair of electrons on the oxygen go back and form a bond with chromium. Pushing out chlorine. Please remember, chlorine is the best leaving group here, so the chlorine is pushed out here and we get this complex here, this complex. And in this case, this chromium group is a very good leaving group. So what happens, but now the chlorine is not very happy about the whole affair. So what it does is, it goes to this is a, please remember, a monochromate ester. It goes and abstracts a alpha hydrogen. So please remember, I said a tertiary alcohol cannot be oxidized if it does not have because it does not have an alpha hydrogen. So for oxidation, this is the oxidation step where chlorine is removing this hydrogen from here. It is acting as a base. This hydrogen is removed as proton, and these bonds are going from here to form a double bond between the oxygen. At the same time, this chromium complex, being a good leaving group, is pushed out, and what we get here is an aldehyde. So this is how all the reagents like Collins reagent, Corey's reagent, pyridinium dichromate act as oxidizing agents, and we get an aldehyde. These reagents do not oxidize a double bond. So what we find is that if we are doing the structure of bent hydrol, it oxidizes to give us benzophenone in 100%, which is a very high yield. And similarly, if we do the reaction again with pyridinium chlorochromate in presence of dichloromethane, again the double bonds are not being oxidized. It is only the OH which is being oxidized to CHO group, and we get an aldehyde. These two are very important compounds. Now we have to talk of other reducing agents like oxidizing agents like PDC. This is less acidic than PCC, and it helps to oxidize those alcohols which are sensitive to acids. And what we find here about PDC is that if we do the oxidation in presence of dichloromethane, then PDC will oxidize the alcoholic group, the primary alcoholic group, to an aldehyde group without affecting the double bond. Whereas if this reaction is carried out in dimethyl formamide, then it will be converted to a carboxylic group. So what we find is that PDC, PCC and Collins reagent act in a similar manner, oxidizing primary alcohols to aldehydes. Now we shall be dealing after the break with the mechanism of Jones reagent and how does Jones reagent act as an oxidizing agent. In this section, we shall be discussing Jones reagent as an oxidizing agent. Jones reagent is chromium trioxide in sulfuric acid and acetone. It oxidizes primary allylic and benzylic alcohols to aldehydes. Please remember, if an aldehyde is capable of forming a hydrate easily or in significant amounts, then Jones reagent oxidizes that further to a acid. So what we have to remember here is, like this alcohol here is a benzylic alcohol. This is a benzyl alcohol. And whether we take potassium dichromate and sulfuric acid and acetone, or we take chromium trioxide with sulfuric acid, the mechanism is going to be basically the same. And this group, OH, is converted to CHO group. But please, to a CHO group. This is a benzylic. But if it was not a benzylic alcohol, please remember it would have been oxidized to a carboxylic group. Similarly, what we find here is that if we take an allylic grouping, what is an allylic grouping? That is, we have a OH which is attached to a sp3 hybridized carbon, and then we have a double bond. This is what is an allylic grouping. And then we do this allylic grouping and we do the oxidation again with Jones reagent. What we find is that these double bonds are not oxidized, 1, and 2, this OH group, primary alcoholic group, is oxidized to give us an aldehyde group. It is not oxidized here to a carboxylic group. But please remember, if we had taken a primary alcohol, then what happens in this case is that this primary alcohol, since we are doing it in aqueous medium in presence of water, it will first be oxidized to aldehyde. Aldehyde will form a hydrate, and then it will be oxidized to a carboxylic acid. So we cannot quench the reaction at the aldehydic stage if we do not have a allylic or a benzylic primary alcohol. Second case is if we take if we take a secondary alcohol, then in that case, secondary alcohol will always be oxidized to a ketone. So now let us look into the mechanism of this reaction. So what happens is, first sulfuric acid ionizes to give us H plus and SO4 minus, and then it reacts, and then this water reacts with, and the H plus from the sulfuric acid goes and reacts with the oxygen here, resulting in formation of a OH group. Then the water molecule reacts again. Water acts as a nucleophile through lone pair of electrons on oxygen. It goes and reacts with chromium here, resulting in chromium acid. And this chromic acid now acts as an oxidizing agent. Similarly, if we do the reaction of sodium dichromate with sulfuric acid, again we will get a dichromic acid which will act as an oxidizing agent. And please remember, we prepare chromic acid in C2. What I mean here by saying in C2 is in the reaction medium. So now what happens is, what we will see here is that this chromic acid will oxidize primary alcohol. Why? Through formation of a monoester, and it will then give us an aldehyde. So what we look here is, what happens in this reaction? Let's look into the details of this reaction. First, let us look briefly into reaction, that this chromic acid here is reacting with the alcohol here. That is, this alcohol will react through lone pair of electrons on oxygen, form a chromate monoester. Why do we call it as a chromate monoester? Because please remember, what is an ester? An ester is a compound in which carbon has a double bond with oxygen, and then carbon is attached to an alkoxy group. So here we can say, instead of carbon, we have a chromium which is attached to a double bonded oxygen, and then here it is attached to an alkoxy group. So we get a chromate monoester here, which again undergoes acid-base reaction to give us a ketone. This was the reaction of a secondary alcohol. Now if we look into a primary alcohol, so what we find here is again that this chromic acid reacts with H plus to form a activated chromic acid. And since it forms the activated chromic acid, now what we find here is that the electron density on this chromium is further decreased. That is, it becomes more electrophilic. The alcohol with the lone pair of electrons on oxygen acts as a nucleophile and forms a bond with this chromium here, resulting in the formation of this complex. Now what happens here is a base comes from, the base can be a water molecule or base can even be HSO4 minus, and it abstracts a alpha hydrogen from here. This is very important, and this goes back into and forms a double bond here between carbon and oxygen. And at the same time, please remember this chromium complex is a good leaving group, and this takes these electrons from here and it is pushed out. So what we have here is now that the base abstracts a proton. Two things, this is a very, very important step. Two things are happening simultaneously. First, the base is abstracting a proton from here when these sigma electrons go and form a double bond here between carbon and oxygen, and this complex with this leaving group, which is a good leaving group, is pushed out. What we get here is a oxonium ion, a protonated one. Now what happens here is when we do the reaction of this molecule, this again a base comes, it reacts again with a base here. That base will abstract a proton from here. Base can be a water molecule, and these electrons will collapse on this oxygen, neutralizing the positive charge, resulting in the formation of an aldehyde. So what we have to remember is this is acting here as a nucleophile. We get a bond formation here, resulting in formation of a chromate monoester. Then a base abstracts a proton, resulting in formation of a double bond here between carbon and oxygen. At the same time, the good leaving group is pushed out, and then this complex ion undergoes reaction with a base when a proton is eliminated to form an aldehyde. But next what we find is that this aldehyde which we have here can react with water which is present in the molecule to give us a hydrate. Now if we have this aldehyde hydrate here, then what we find is that this lone pair of electrons on oxygen again can react as nucleophile. Again the same mechanism all over again, that this oxygen will be protonated. It will be an activated chromium complex, chromium acid. This will form a bond here, resulting in formation of a monoester. Then what happens is when we have this monoester, a proton is extracted from here, and after the extraction of proton, what we have is from here resulting in formation of a C double bond O here, and this then results, and at the same time this is pushed out from here, this good leaving group, and what we get here is a carboxylic acid. So what we find here is that if we do oxidation with Collins reagent, then we are getting an aldehyde, whereas if we do the oxidation with Jones reagent, then we are in presence of water, then what we are getting is an aldehyde which is further oxidized to an acid. So another oxidizing agent which is of interest is manganese dioxide. This oxidizes allylic alcohols to corresponding aldehydes or ketones. So what we find here is that this is an allylic alcohol and this is a primary alcohol. Please remember, primary alcohol will be oxidized to an aldehyde and a secondary alcohol is oxidized to a ketone. So this is an allylic alcohol. Here again the double bond is not affected. This OH group is converted to is oxidized to a CHO group. Why do we call this as oxidation? what we find here is that when we are converting this OH to a CO, what we find here is that there in an alcohol, there is one bond between carbon and oxygen. Whereas when we talk of an aldehyde or a ketone, there are two bonds between carbon and oxygen. So a bond is increasing, hence the compound is undergoing oxidation. So from this primary alcohol, we will get an aldehyde. Whereas if we talk of a secondary alcohol here, then what we find in this case, in secondary alcohol, this OH will be oxidized to a ketonic group. That is, a steroid which is estradiol will be oxidized to estrone in the living system. These were the oxidation reactions of alcohols by which we could prepare aldehydes and ketones. Please keep in mind that if we use strong oxidizing agents, then primary alcohols will be oxidized to carboxylic acids, whereas secondary alcohols will be oxidized to ketones. And if we are taking Collins reagent or PCC or PDC, then in that case, we will get an aldehyde from a primary alcohol, whereas if we use potassium dichromate acidic or Jones reagent, we will get a carboxylic acid, because oxidation cannot be stopped at the aldehydic state. Now the next method of preparation is that we can prepare aldehydes and ketones from 1,3-dithiene. Now if you look into the structure of this dithiene, what we find is that these two hydrogens here are acidic in nature. Why are they acidic in nature? That is because they are attached to two electron withdrawing sulfur groups. Not only this, once we remove a proton from here, we will get an anion here, and this anion is very stable because it is attached to two electron withdrawing highly polarizable sulfur atoms. So these two sulfur atoms are polar in nature and they will stabilize this carbanion. So what we find is that if we treat dithiene with a strong base like butyl lithium, then what we find in butyl lithium is, since it is an organometallic compound, this butyl will have a negative charge and lithium has a positive charge on it. So what this C4H9 does, it abstracts a proton from here, this proton, which I have shown in red color, resulting in the formation of the butane. At the same time, what we get here is an anion. Now this anion will react with a molecule of alkyl halide by SN2 mechanism, resulting in the formation of thioacetal. We get a thioacetal here, and then when we do the hydrolysis of this thioacetal, we get a aldehyde. So what we see here is, this is undergoing an SN2 mechanism. This will react from the backside on this alkyl halide. The alkyl halide taken here is a primary alkyl halide. We get a thioacetal here, and when we do the hydrolysis of thioacetal, we get an aldehyde. Alternatively, if we want to prepare a ketone, then what we can do is, this can be reacted further. It still has, please look here, an acidic hydrogen. This hydrogen is still acidic in nature. This will again react with the base, butyl lithium, and we will get an anion here, and then this anion will react with an alkyl halide, resulting in formation of a new thioacetal with two alkyl groups, and then when we do the hydrolysis of this compound, we will get a ketone. Now if we want to prepare an unsymmetrical ketone, that can also be done very easily. How do we do that? We know that these two hydrogens are acidic in nature. So first reaction we will do with lithium, butyl lithium. When we do this, we get an anion, and then we are treating that anion with benzyl bromide. When we do that, we have introduced a benzyl group here. Now in the second step what we do is we remove this hydrogen from here as proton, and then we are doing the reaction with bromomethane. When we do the reaction with bromomethane, what we get here is a methyl group. So what we've done here is we've done the reaction in two steps. In the first step we've introduced the benzyl group, and in the second step we have introduced the methyl group, resulting in an unsymmetrical thiene. Now this thiene, acetylthiene, undergoes hydrolysis and gives us a unsymmetrical ketone. So what we have observed, that if we take dithiene and if we just do one reaction, that is one series of reaction with a butyl lithium and an alkyl halide, followed by hydrolysis, we'll get an aldehyde. Whereas if both the acidic hydrogens of dithiene are replaced with an alkyl or an aryl group, and then we do the hydrolysis, then we will get a ketone. And this is again a very good method for preparation of aldehydes and ketones. We know that when we heat calcium salts of carboxylic acids in absence of oxygen, it is known as pyrolysis. And what we find is this is also known as dry distillation. So when we do pyrolysis of calcium salts of carboxylic acids, we end up getting aldehyde or a ketone. Now what we'll get will depend on the structure of the starting compound, that is the calcium salt. If we will take calcium formate and we heat calcium formate, we get formaldehyde. If we will take calcium formate and calcium acetate, we'll get acetaldehyde. If we take calcium formate and calcium benzoate, we get benzaldehyde. And if we heat calcium acetate, we will get acetone. Similarly, calcium benzoate will give us benzophenone. So what we find is that when we heat these calcium salts, they lose a molecule of carbon dioxide, that is, they undergo decarboxylation, at the same time forming an aldehyde or a ketone. Let us look into the mechanism of this reaction by doing ketonic decarboxylation of adipic acid. This adipic acid is 1,6-hexane dioic acid, and what we see in this reaction is it involves three steps. The first one is the deprotonation, second is decarboxylation, and third is then the attack of the carb anion, or nucleophilic attack of the carb anion on the carboxylic group. So what we find here is that when we do the reaction of adipic acid in presence of a base, it removes this H plus from here. It undergoes, that is, this adipic acid is undergoing deprotonation to give us this anion. Now what happens in this case is that this oxygen, this bond from here goes back here, and this will pull the electrons from towards itself. We'll get a negative charge, and this carbon dioxide is given off when we heat it to 250 to 280 degrees Celsius, resulting in this anion. Now what happens is that this anion from here acts as a nucleophile, and it makes a bond with this carbon here, which is electrophilic in nature, because this carbon is electron deficient, because it is attached to an oxygen by a double bond, as well as it is attached to an OH. So it is electron deficient. When this nucleophile approaches, the pi electrons move towards the oxygen here, so we get this intermediate here. But now this is unstable. What happens is that these electrons go back, forming a double bond between carbon and oxygen, and this OH is pushed out, resulting in the formation of cyclopentanone. So in this case, what has happened is, since it is undergoing decarboxylation, we are getting a ketone which is having 1 carbon less than the starting compound. Now we shall discuss some special methods for preparation of aldehydes, that is, those methods by which only aldehydes can be prepared. The first method of preparation is by reduction of nitriles. We can do reduction of nitriles by SnCl2 and HCl. This was proposed by Stephen, because normally what we see is that if we do reduction of a cyanide with lithium aluminium hydride, which is a strong reducing agent, it will reduce this triple bond all the way to a amine, that is, an amine will be formed. Whereas when we do the reaction with SnCl2 in presence of HCl, what happens is that this reacts, SnCl2 reacts with HCl to give us hydrogen, nascent hydrogen, which then adds to this carbon and this nitrogen. Now this nitrogen is more electronegative and it will pull the electrons towards itself. So this is how the reaction starts. Now this reacts with HCl to give us a aldeamine. This amine, or we'll get a aminochloride here, and this aminochloride on hydrolysis gives us an aldehyde along with ammonium chloride. So this is what we find here is that if we take acetonitrile and do the reaction with SnCl2 and HCl, first we will get a aminochloride here, acetyl aminochloride, which on hydrolysis will give us an aldehyde and ammonium chloride. The next very, very important method of preparation is Rosamond reduction of acid chlorides. So what we do here again is we pass the vapors of acid chloride and hydrogen gas over palladium, which has been poisoned by barium sulfate. So why do we do this reaction? Why do we have to poison this palladium catalyst? Please remember, the reaction mechanism is somewhat similar to what we do for the reduction of alkenes. So what we find here is, but please remember here, when we do the reduction of alkenes, then in that case, hydrogen is added across the C double bond C. Here hydrogen does not add across CO, because this bond is a very strong bond and it is difficult to break this bond. So what happens here is, since we are doing reduction, this Cl, as we see, if we are taking acetyl chloride, we are getting acetaldehyde. So what are we doing in this reaction is, we are replacing this Cl with a hydrogen here. So what we have to do is, now so from this we can make out what will happen is that the bond between this C and Cl will break. Why does this so happen? Because the bond between C and Cl is weak. First, there are lone pair of electrons on oxygen, which I have not shown here. Please remember, we have 2 lone pair of electrons on oxygen and 3 lone pair of electrons on chlorine. So what happens is, there is repulsion between these electrons and this bond, and because of this, the bond becomes weak. Second, what we find is that this bond becomes reactive. This CCl bond becomes reactive. And second thing what we know is that carbon is present in the second period, whereas Cl is present in the third period. So the overlapping here, the bond here formed is a weak bond. So this bond will break. So what we are doing is, now when we pass hydrogen through this in presence of palladium, what happens is hydrogen breaks down to give us, and one hydrogen goes and adds here, the second hydrogen adds here to give us acetaldehyde. The reason is, why are we taking palladium? What is the need for taking palladium here? Palladium here acts as a catalyst, and we know it is a transition metal. So it is quite porous. So what happens here is hydrogen adsorbs onto it. At the same time, this is, since aldehyde, this acetyl chloride, since it is rich in electrons on oxygen and chlorine, it also adsorbs to the positive charge, to the electron deficient orbital of palladium, and we get a bond, and then hydrogen comes in, adds here, and we get acetaldehyde. Now the question arises that why does acetaldehyde not reduce further to an alcohol? The reason being, if you look into the structure of acetaldehyde, then it has only 2 pair of electrons on oxygen. So its bond formation with palladium is not very strong. Since it has been, the palladium has been, now this is the function of BaSO4. BaSO4 has poisoned palladium, so all the sites are not available, and we know acetyl chloride is more reactive towards palladium. It will adsorb, whereas acetaldehyde being less reactive, there is no less surface area available on palladium, and it will not be able to bind there. Hence, acetaldehyde will not be reduced further to an alcohol. So when we do the reaction with Rosamond reduction, we get an aldehyde. The second thing which is very important about this reaction is that this will not reduce a double bond here. Since the catalyst is poisoned, it will only reduce acid chloride to a aldehyde. So if we want to prepare an unsaturated aldehyde, what we can do is we can take an acid chloride and do the reaction with PD, BaSO4 and hydrogen, when we will get an unsaturated aldehyde. We can do reduction of aldehyde of acids also, but that reaction is not very convenient, because we know that when we do the reduction of acids, what happens is first we will get an aldehyde. But as I have said that these aldehydes are more reactive towards reduction as compared to acids, hence they will be reduced all the way to the alcohol. So what can we do now? We can modify this acid and convert it into acid chloride, and then do the reduction of acid chloride further to an aldehyde, which we will be discussing in our next lecture. Thank you.
With this note, thank you, ma'am. Thank you so very much for giving us a productive session. And dear friends, you are requested to give your feedbacks on this particular lecture, as well as your questions are also welcome. So do write to us at info.cec@nic.in. We would be meeting again very soon and would be discussing on another topic. Till then, take care. Goodbye. Thank you, ma'am. Thank you so very much.